This is 27.6. And in this problem we have a conductor of a non-uniform cross-section with 5 amps going through it. And let's see, so it looks something like this. It has a circular cross-section. Circular cross-section here, radius R1, and then it gets larger in cross-section as you go out here, and here it's at R2. And the length, the current going through this entire thing is 5 amps. And that's all we know, that's all we need to know. So, first question, what is the magnitude of the current density? What is the current density at the first face, R1? Let's see, what is the magnitude of the current density across A1? Right? So this is R1 and R2 because this is area A1 and A2. Okay. So the current density is just the current per unit area. The key to this problem is to know that if current flows through here, the same current flows through here. Okay, so it's the same number of electrons. If we have electrons or if we have charges flowing through this thing, then the number that cross this plane per unit time has to be the same as the number that cross that plane per unit time. If we're going to conserve charge, and if they're all going to flow together. So the current is the same everywhere, but the current density will change, the current per unit area. So first, let's just calculate the current density here. It's just the current over the area. So it's just 5 amps over pi times the radius squared, and they tell us that R1 equals 0.4 centimeters. So it equals 4 millimeters. So if we're going to do this all in MKS units, that's 4 times 10 to the minus 3 meters. So you just calculate that, and it's 9.9 times 10 to the 4th amps per meter squared. 9.9 times 10 to the 4th amps per meter squared. Question B, is the current at A2 larger, smaller, or the same? Okay. So B is I at A2. I at A2 compared to I at A1, larger, smaller, the same. Like I said at the beginning, current is the same throughout a circuit. If you have a wire carrying a current, the current is the same everywhere. So it's the same as IA1. It's 5 amps everywhere. C. C, this one had a lot of questions, I can't quite remember them all. C is the current density at A2 larger, smaller, or the same. So the current density will change. Of course, that's the current per unit area, so clearly then J at A2, if we divide by a larger area, it'll be smaller than A1. Then J. Okay. Let's see. Same, smaller, A, B, C. That was part C. D. Okay. Now we assume that A2 is 4 times A1, and we want to get all the properties at A2. So if A2, the area A2 is 4 times A1, the question is first, what is R2? Okay. So you can just say A2, which is pi R2 squared, equals 4 times the area of A1, which we calculated here, but we never actually wrote it down. So we can just write this again: pi times 4 times 10 to the minus 3 and negative. Okay. So that's one way to do it. And then, since we didn't get a number here, we just do it this way. We just cancel the pi's, and we multiply that out. 4 times 4 is 16, times 10 to the minus 6, times 4 is 64, times 10 to the minus 6 meters squared. R2 squared equals that. So R2, you can actually do it without a calculator. That's 8 times 10 to the minus 3 meters. Or you could have probably done that one just by looking at it and knowing that the area goes as the radius squared. So if you multiply the area by 4, you multiply the radius by 2. And sure enough, we went from 4 millimeters to 8 millimeters. So anyway, there's R2. Part E, the question was, the question is, what is the current? The current is the same everywhere, 5 amps. In part F, the question was the current density at A2. So at A2, current density is going to be the same thing. J, this was at A1, so J at A2 is going to be 5 amps over pi times 8 times 10 minus 3 meters squared, which is going to be 2.5 times 10 to the 4 amps per meter squared. Pretty much it's going to be a quarter of this value. This is 10, more or less. 10 divided by 4 is 2.5, because the area went up by a factor of 4. That's it. I'm going to go find some less squeaky chalk.